Hey there, welcome back to Imperatively Functional, your go-to channel for bridging the gap between software theory and hands-on practice. Today, we are tackling something you won't find in your everyday game development tutorials, an explosion effect so dynamic, it literally breaks apart. And guess what? We are doing it all through recursion, specialized sprite manipulation, and shader magic. Here's your roadmap for today's journey into code wizardry. Setting the stage with recursion, generating rectangles of varying sizes through a custom recursive algorithm, crafting region-specific sprites, how to carve out pieces of your main sprite texture based on the generated rectangles, the finishing touch, using shaders for dissolve effect that adds depth to your explosion. Let's kick off with the recursion. Now, the algorithm we'll use here is no vanilla recursive function. It's tailored for geometric decomposition, breaking down our tarot sprite into a series of smaller, randomly sized rectangles. The end goal? A sprite that does not just vanish, it disintegrates. What is recursion? Imagine a set of Russian nesting dolls, where each doll contains a smaller version of itself inside. To fully open all the dolls, you start with the largest one and proceed to open each smaller doll within it. Repeating the same action, open and remove the smaller doll until you get to the smallest one, which doesn't contain any more dolls. Recursion in computer science is quite similar. A recursive function calls itself with modified parameters, and this repeats until a base case is reached. The base case is like the smallest doll which doesn't contain another doll. It's the condition where the function doesn't call itself again. Let's look at tarot.gd file. In the _ready function, we first connect receive damages from player event so that the tarot is able to receive damages. Then we call divide rectangle method to calculate a list of smaller rectangles. Let's see how this function is written. The divide rectangle function is a recursion algorithm designed to subdivide a given rectangle into smaller rectangles. The end result of these subdivisions is stored in the rectangle member variable. The function accepts a rectangle and determines its width and height. Random mean width and mean height thresholds are also calculated. If the rectangle width and height are less than the calculated minimums, the rectangle is deemed too small to further divide and is appended to the _rectangles list. If the rectangle is large enough to be divided, one of the following occurs. It is divided either vertically or horizontally based on a random decision. Random f less than 0.5. If it is too narrow but long enough, it is divided vertically. If it is too short but wide enough, it is divided horizontally. Randomness plays a significant role in deciding the size and orientation of the subdivisions. This will make each division sequence unique to create a shattering or fragmenting effect. The actual subdivision occurs by calculating a random point, cut x or cut y, within the rectangle, taking into account the minimum width or height. The rectangle is then split into two at this point. After splitting, the function is called recursively on the two new rectangles. The leaf rectangle, those that cannot be divided further, are stored in the _rectangles list. Next up, let's focus on the sprite creation process. You will see how we can take the coordinates of the rectangles generated by our recursion algorithm and map those to the original sprite texture. This isn't your everyday sprite handling. It's about giving you the ability to manipulate very specific regions of your sprite to create a more realistic disintegration effect. OnAnimation player animation finished is invoked when explosion animation on the animation player node finishes playing. Remove child hitbox. This removes the hitbox child node, effectively disabling any further collision detection for the turret. Visible equals false. This makes the current turret invisible post-explosion. Max time equals 0. Initialize a variable to track the longest time any fragment will take to dissolve. For rect in rectangles, loop through the rectangle array underscore rectangles that hold smaller pieces of the turret's region. First, create a new sprite and configure its various properties. 1. Set the texture to the turret's original texture. 2. Enable texture region for 2D sprite. 3. Sets the texture region to the current rectangle. 4. Allows the new sprite's position to be global. Y velocity calculates a random initial velocity speed for the fragment is clamped between 10 and 100. Removal time randomly select how many seconds it will take for this fragment to dissolve completely. Max time keep track of the longest removal time among all fragments. Sets up the shader for dissolving effect. Creates a new shader material. Sets the time to fade shader parameter to removal time. Assign the preloaded shader to it. New sprite.material equals shader material. Apply the shader material to the new sprite. Then position the sprite based on a formula that considers the original turret's position, the sprite size, and the rectangle's position and size. This will align the individual piece perfectly to the original turret. Next, add this sprite to the root of the scene tree. Create a JSON object to store the sprite's data to sprite underscore data for future processing. Post loop cleaning up. Sets up a timer to execute the underscore kill function, which will remove the turret completely. The timer is set to fire after the longest fragment's removal time. So essentially, this function handles what happens immediately after the explosion, which includes removing the turret from the play while simultaneously scattering its smaller pieces. And lastly, we'll delve into shaders. Now you could stop after the sprite breaks up. But why not go the extra mile? A dissolve shader will help those broken pieces fade away in style, instead of just popping out of existence. Let's look at the shader code. We set shader type to canvas item to indicate that is intended for 2D rendering. Declare an external variable called time to fade that sets the fade out duration with a default value of 5 seconds. The void fragment function serves as the main function and is executed per pixel. First, we retrieve the current pixel color, then we record the elapsed time and calculate the new alpha value based on that time. The alpha value is modified but clamped between 0.8 and 1.0. Finally, we set the pixel color to text color. The shader gradually decreases the alpha value of each pixel over time with a lower bound of 0.8 to produce a fade-out effect. Finally, let's look at process function. It iterates through the sprite data list, specifically looking at sprites not marked as removed. it performs the following tasks. 1. Adjusts the sprite Y position based on a constant Y velocity and the frame's delta time. 2. Reduces the sprite's removal time by the delta time. 3. Checks if removal time is less than or equals to 0. If yes, marks the sprite as removed and queues it for deletion. Is effectively handling sprite positioning and managing their lifetimes based on a countdown timer. If you found this content valuable, make sure to subscribe for more, share it to spread the knowledge, and comment below to join the discussion. For a deeper dive, check out our Discord server and access the source code linked in the description.